With these two, we arrived to the last talk of this morning. The speaker is Drazen Dagan, or Glavan, sorry. And he will tell us about even photons break the Sitter symmetry. I don't know.
All right, good afternoon, everyone. Good to see you all. Today, I'll tell you a little bit about some work from last year that I did in part with Tomislav Prokopec. He's there in the audience as well. And it's about how even photons must break the Sitter symmetry. And in particular, it's how photon propagators cannot respect the Sitter symmetry in the Sitter space. This is a fact that's seemingly been overlooked by for quite a long time by previous works. And I say this in no way to criticize previous works. I only say this to emphasize that it is a rather subtle issue and that the Sitter space quantum field theory still holds quite some surprises compared to its flat space counterpart. So maybe the most fair first question one should ask is why even consider photons? What's so special about them? In fact, they shouldn't do anything in the Sitter. In fact, they shouldn't do anything in Robertson-Walker or cosmological spacetimes. And that's very simple to argue. In fact, photons are conformally coupled to gravity. And Friedmann-Lemaitre Robertson-Walker, or FLRW for short, spacetime is conformally flat, which means that in 4 spacetime dimensions, photon is described by the very same action, which now shouldn't contain this G, this is 1 in flat space, by the very same action as in flat space, meaning its dynamics is exactly the flat space dynamics. And we know what flat space dynamics of photons is. In particular, we know there are 2 physical degrees of freedom, the 2 transverse polarizations, and we know how they propagate. Well, that is all true. However, photons do couple to other things, and other things, other fields, can actually be rather important in inflation and can sense the expansion, the rapid expansion of inflation, even at 3 level. Such fields are non-conformally coupled fields, and there's 2 examples of those. It's scalars and gravitons. Both of them experience what is usually called the gravitational particle production, which in this case means that they get a huge enhancement of their infrared sector. This is, in fact, what is behind the scale invariant power spectrum of both scalars and tensors in cosmology. And presumably, they couple to photons. Well, at least gravitons do, because gravity couples to everything universally, but also scalars do couple to photons in a given model. So what I devote considerable part of my research is to investigating the effects that fields such as scalars and gravitons can mediate to other fields like the photons that don't sense the expansion themselves, but their conformality is broken by quantum loop effects. And in that way, they do sense the expansion, and they could potentially serve as probes of early universe inflationary physics. So to that end, I'm interested in computing dimensionally regulated loop corrections to various quantities, such as endpoint functions in inflation. Those computations, however, are not that palatable always, and simplifications are rather welcome. And the usually employed simplification, which is usually also very good, is to take an exact de Sitter space. And by that, I mean precisely the Poincaré patch of de Sitter, so expanding cosmological patch defined by a constant Hubble rate, which also implies a vanishing first lower Rolle parameter. The scale factor, as a reminder, goes exponentially with physical time or like 1 over conformal time. And this is usually, well, this is in very many cases a very good approximation of primordial inflating spacetime. And in practice, it's a very good simplification, as the Sitter itself is a maximally symmetric spacetime, and it admits in 4 spacetime dimensions I believe, 10 isometries. And usually the more symmetries one has, the simpler the problem gets. So in the sense that it's maximally symmetric space, it is similar to, how we approach flat space physics, which happens in Minkowski space, which is also maximally symmetric. And there we know that Poincare symmetries are a fantastic organizational principle for computations. So maybe one can approach the sitter space computations in the very same way. So, but before, one needs to build basic ingredients for perturbation theory for computing loops, and those are nothing else than propagators, or in particular non-equilibrium quantum field theory, there are a number of two-point functions that themselves then form the loops. So the two-point functions that we can form are well, maybe you can remember only two, the Feynman and the Whiteman one, and the labeling follows the Schwinger-Keldysh polarity labels. The one is a time-ordered product, and the other one is an unordered product of field operators. And these are the objects that I want to talk about today. However, at this level, this is just symbolic, because if we were to do any computation in quantum field theory and gauge theories, such as electromagnetism or the photon, one necessarily has to fix the gauge. Now, there's nothing really that physical about fixing the gauge. However, it makes a big difference which choices you make, as it might make your life much easier. And perhaps the obvious idea for fixing the gauge is to fix the so-called covariant gauge. This is a gauge that is usually defined by adding the so-called gauge fixing functional to the gauge invariant covariant Maxwell action. This sort of gauge fixing should be distinguished from the so-called exact gauges, like the Coulomb gauge, where you write down an exact gauge condition, solve for the extra degrees of freedom that you have. However, even though there's nothing wrong with that, even in flat space, it's true that a gauge such as a Coulomb gauge is a much more difficult thing to implement or to work with rather than a covariant gauge such as this one. The same applies in the sitter space. So I want to talk about a propagator for the photon in this particular gauge. One particularly appealing feature about these gauges, they're also sometimes called covariant gauges or average gauges, or I prefer the term multiplier gauges, is that they come with a free parameter in them, and that free parameter in practice allows you to test some of your results. If you were to compute an observable should be something that is gauge independent and should never depend on a free gauge fixing parameter. Now in flat space, this is not really all that important, since you mostly compute S matrices, and that thing will be gauge invariant for sure. In the sitter space, the question of observables, and in particular, in more complicated gauge theories such as perturbative quantum gravity, this issue of constructing observables is not that straightforward, and it's very useful to have a parameter that allows you to check your results. Very well. So one thing that happens in this gauge, that the two-point functions, so this A and B stand for those polarities. I will not write them in all slides, only when it's strictly necessary, but usually they're just implied. The propagator satisfies the following equation of motion in this gauge, and this is the contribution that comes from this part. And you will please excuse me for forgetting to write a G rho nu metric on the right-hand side for indices to work out. Very good. So essentially, what you need to do is solve this equation to obtain the propagator, and a number of people in several pretty good papers have done this over the past. They've used different methods, but pretty much all of them can be encompassed by the approach originally implemented by Allen and Jacobson. And that is, since you have a field in a de Sitter spacetime, which is full of symmetries, why not just assume that your solution respects all those symmetries? That's a rather constraining assumption in de Sitter, as it limits your ansatz to the following form, which is constructed out of two tensor structures made out of objects which are some sort of de Sitter invariant lengths. They're not really geodesic lengths, but are basically rescaled Poincaré distances. You can use that to construct the tensor structures, and then there are only two free functions to determine from solving the equations. And one can do that just fine. And one obtains the solutions for the structure functions, which are expressed in terms of these calligraphic F functions, which you can recognize as a scalar propagator or a scalar two-point function for a particular mass. The interesting thing to note here is that I've shown you a de Sitter invariant ansatz for this thing, and I've shown you a solution for this thing, and it's a perfectly good solution of the equations of motion. That's why this problem is quite subtle, because this really is the solution to the equations of motion. However, there seems to be some problems when you try to compute things using this propagator. And maybe the simplest example, simplest non-trivial example one can look at is the energy momentum tensor. It can be seen as it can be viewed as a graviton tacpole. Gravitons coupled to the energy momentum tensor, and it's a one loop observable, and it's formed out of a single propagator. So essentially you need to take some coincidence limits. But there are two different ways in which one can define the energy momentum tensor. You can define it as a variation of the gauge invariant Maxwell action, or you can define it as a variation with respect to the metric of the gauge fixed action. So the two differ by this red term here. Now, what needs to happen is for these definitions both to give the same result. And once you go through the computation, you actually find that the Sitter values are 0 for the gauge invariant definition, and the non-vanishing cosmological constant type contribution for the gauge fixed action. Now, I call this a problem, even though it's not an obvious one, because there is no dependence on the gauge fixing parameter xi. But which value do you pick? They should both give the same result. So it's a good idea to examine in more details the procedure of gauge fixing and the contribution of the gauge fixing part that's not vanishing. And there are multiple ways of doing this. One can do this in a canonical formalism just fine, but it's a lot more complicated. The more maybe the simpler and the more intuitive way to derive this is to just use the BRST formalism, where in addition to, even though this is a linear theory, but in addition to the gauge fixing term, you do need to add the Fadeev-Popov ghost action with these C bar and C Grassmannian fields, and they satisfy their own equations of motion. And they do contribute to the energy momentum tensor. So this is a peculiarity of, including gravity, because the variation with respect to the metric receives contributions from this part as well. So computing this boils down to evaluating some coincidence limits of photon propagators and of the ghost propagators. And they satisfy, by the way, the equations of a massless minimally coupled scalar. So these terms are colored because the red ones end up canceling between themselves and the blue ones do. What remains is this one here. Now, why do these ones cancel? That is actually a consequence of a Ward-Takahashi identity, actually a derivative of a Ward-Takahashi identity. And by the same reasoning, the first term should vanish as well, because it's a different double derivative of a Ward-Takahashi identity given here. But this one actually doesn't when you compute it. So this is where the problem is. The problem is that the Ward-Takahashi identity by itself explicitly breaks the Sitter invariance, and it breaks it because the ghost propagator is the same as the propagator of the massless minimally coupled scalar, and there are no de Sitter invariant solutions for a massless minimally coupled scalar. This has been shown quite some time ago. The effect of that is that when you take the left and the right-hand side of the Ward-Takahashi identity. The right-hand side receives a contribution which explicitly does not depend only on y and its derivatives, but rather it breaks de Sitter invariance. So what the actual photon propagator has to satisfy is not only the equation of motion, which is again missing the same metric, but it has to satisfy the Ward-Takahashi identity. And the right-hand side, the ghost propagator, has to satisfy the equation of a massless minimally coupled scalar. And in that sense, the requirements we get from gauge theory are requirements that prevent even photons from respecting the Sitter symmetry. Very well. And this is the reference of people who have shown that there are no de Sitter invariant solutions for scalar propagators. So when you actually take all of the equations into account and you solve them, as a result, you get the known result from the literature supplemented by this part, which explicitly breaks the Sitter symmetries. In particular, it preserves dilations, but it breaks special conformal symmetry. And this is our contribution to the propagator. It should be noted that this piece is a homogeneous solution to the equations of motion, and hence you would never ever see it by just solving equations of motion. And in that sense, when you include this term, it resolves the issue of the expectation value of the energy momentum tensor. And in addition, as another problem, it changes completely the infrared behavior of the propagator. The Sitter invariant one actually doesn't asymptote to zero for large separations, while the de Sitter breaking one does asymptote to zero. And those are pretty much all of the things that I wanted to show you today. And just to maybe conclude with one or two words, maybe it's a good idea to examine how we approach symmetries in the Sitter space, because this is yet another example where one has to be rather careful when implementing them. Now, this is completely contained in the gauge sector, yes, at the linear level, but once you start computing loops, the difference between a physical degree of freedom and a gauge degree of freedom gets a little bit blurry, so you better get things correct. Otherwise, you might get the loop contributions a little bit off. Thank you.
Questions?
Hi, thank you a lot for the talk. I got a question. When you impose that the propagator is invariant under the seated symmetries, you are referring to the 10 isometries, right? Not because if you look only for the relevant part for inflation, you have less isometries, right?
Oh, that is correct. So all the computations pertain to the exact de Sitter limit as a simplification of as a toy model for inflation.
And do you believe the result would hold if you look for a state that is less invariant, that contains only the isometries relevant for inflation?
In fact, the massless minimally coupled propagator that I used for the ghost is precisely that kind of propagator. There, the impossibility of maintaining de Sitter symmetries is a physical impossibility because there is no gauge symmetry, so it's a physical statement. That propagator only maintains cosmological symmetries, even in de Sitter spatial translation and rotations, and breaks both, I think, conformal symmetries and dilations. This one breaks one symmetry less. So in that sense, this is well adapted for extending it to realistic inflationary spacetimes. But there you would never even ask this question because it's irrelevant. You never expect the full symmetry. However, everything is going to be much, much more difficult.
Thank you.